Hi, welcome back to Statics 1. We're going to talk today about simplification of complex systems. Complex systems in the sense that they have many forces or moments applied to your system. What we're going to do is simplify them, which will allow you or simplify the process of evaluating the forces on our external supports. And we're going to talk about that more later in the term. So let's get on to this. We're going to talk about simplification. And what we're going to do is we're going to create equivalent systems. They're only equivalent from the perspective of our external supports. So let me explain what that means. If you have a rigid body and it has these, this is a beam. Here we have a beam. And I'm actually going to have this beam being supported instead of our typical support would be like a hinge support, a roller support, a fixed support. There are other supports. Instead, we're going to have people down here supporting this thing. And he's got, not floating in air, he's supporting it. And then there's someone over here. Let's see if I can do this. Up. And this person is also likewise on this end. And these people, they can only look out. They can't look up. They can't see what kind of force system is acting on their beam. So it could be something very complicated. We have two forces. We have a moment couple. And that's what we really have, forces and couples. So we have two forces at different angles. And what we want to do, and I'll add another force here and one here. Maybe that direction. Maybe we have a distributed load. We want to reduce this all to one force and one moment, at least in the first phase. And that's what we're going to talk about today. In the next phase, in other words, in the next chapter of the textbook, they're going to discuss coplanar systems where you can actually reduce these complex systems to just one force, just one applied force. So we'll talk about that. So here they are. Here we have these people supporting this thing, and here's our simplified system. Again, we have the same people here supporting this. Here's one on this end, and there's someone on this end supporting this beam, and they're standing on the ground. They can't. And so we're going to reduce this to one force and one applied at some, and typically we say it's at point O. So you apply a force and a moment at point O. These people, they can't look up, right? And if you ask them, what is the system of force? Is the system of forces different in this case or this case? They would go, we don't know. It feels exactly the same. So that's the sense in which it's equivalent. It's equivalent in the sense that the external supports, the forces provided by the external supports are going to be identical, although you've reduced it from many forces and moments to just one force and one moment. So equivalent meaning the external forces, and sometimes we're going to call them support reactions. We're going to have like a whole chapter just dealing with support reactions. R, X, N. Reactions are the same. External forces, support reactions are the same. There's one other sense that could be equivalent, but we as civil engineers don't deal with that. If instead of a static beam that's just sitting there, first of all, it's rigid and it's just sitting there. Imagine we have a beam that's floating around. Maybe it's in outer space and it's floating around and it has some motion, acceleration, velocity. It's moving across through space, and this means it's rotating. And if the system, the forces operating on it were equivalent, it would be rotating and moving linearly at the same velocity and acceleration. So that's one other way that it could be equivalent. But that's not really what we're dealing with here. In this case, it's more dealing with these external support reactions that are holding this thing up and keeping it from moving. So they're preventing motion, but we have these forces that they're exerting to do so. And that's that notion of equivalence. So how do we calculate equivalent systems? So what I'm going to do is I'm going to erase the board, and then we'll come back and we'll talk about how that's done. All right, so now we're going to talk about how simplification is done. Imagine we have some beam. In this case, I'll get rid of our little person. That's a hinge support. We'll talk about that later. This is a roller support. Hinge supports can exert forces laterally and vertically. Rollers only vertically. Not really, don't worry about that for now, but we have forces. Maybe we have N forces. So we have N forces. And we're going to have also a number of couples here, force couples, which are creating moments. And we'll say we have M couples. To find the simplified system, we're going to add up all the force vectors and come up with the resultant vector. Sound familiar? We've been doing that almost since day one in this class. We're going to take all the moments caused by those forces, by those N forces, we're going to add them up, and we're going to also add, however, the moments caused by the couples. So we end up with a resultant moment, and that essentially is our simplified system. So what we can do is, and I'll use the notation they use in the book, FR, which is resultant force vector, evaluated about 0.0. And you can do it about any 0.0 you want. Typically, we sometimes will pick up 0.0 maybe at the end. And here's where we're going to have our simplified system, which will be just one force and one moment. So we have N forces, M couples, reducing down to one moment and one force. So anyway, so here's our force vector, and that's going to be equal to the sum over our N forces. So I equals 1 to N of F of I vector. Okay, so we're just going to add up all the forces. That's our resultant force vector. Easy. We've done that all along. Now we're going to talk about our moment, our resultant moment, MR, about 0.0. And that's going to be equal to the sum of the moments, about 0.0, from these N forces. So I'm going to put I equals 1 to N. And then we're going to add to that the sum of the moments from the couples. So that'll be I equals 1 to M. These are from the couples. Okay, that's all you have to do. Now, if we're in a coplanar system, I'll write that out. And if we're in a coplanar system, we can do it just f of x, f of y, and then we can write only the magnitudes of the vectors, because in a coplanar system, we know the vectors are the moment vectors are out of the page or into the page, as long as we have a coplanar system. And they're out of the page if you're counterclockwise, positive, we call that positive vector, and negative if you have a clockwise, and that would be into the page. So we can write over here, FRX, so it's a resultant vector, x component equals the sum, it's still I equals 1 to N, FIX. You notice I don't have a vector, it's just the component in the x, or the magnitude of the x component. So you can write FRY equals the sum, same thing, over a summation of N, FI Y component. And then lastly, we can just write the same equation here, but we're going to write it without the vectors. We're just going to write magnitudes, because we know all the vectors are either into the page or out of the page. We know the direction, essentially. So we have MRO equals, same thing, summation over n forces. So we have the summation over m forces where we're evaluating that moment. I guess I should have a subscript I here as well. And then I can add to that the summation over m for all of the couples. So again, just like here with couples, these are our force couples. These are the moments related to just the forces, and these are the moments related to couples. I'm going to erase the board. I'm going to show you a quick example, and that'll be it. All right, so I'm back. So we're going to look now at an example of, and this one happens to be in a coplanar system, so I kept our equations here for our simplified vector magnitudes. So let's look at that. So I'm going to write this as, we have a very simple structure system here. Looks like that. And this is 4 meters up and 2 meters across. That's about 2 meters. I mean, trying to make these to scale to the extent we can. And it has 2 forces acting on it and 1 moment couple. And the first force, they're both 500 Newton magnitude, only this one, I'll do it in another color. Let me do it in green, too late, but let's try this. That worked. Green, 500 Newtons. And we'll make this a 3, 4, 5 triangle, and that helps us to get the slopes. It's actually much easier than if you have the angles specified, because we know the ratios right away. And on the other side, I'm going to have 500, and this one's also 500 Newtons. The length of that vector should be the same as the length of that one, approximately. I mean, it should be precisely if we could draw, precisely if we took the time. Also, 4, 3, 5 triangle. And then we have a moment acting, a couple moment acting right here, 200 Newton meters, and it's counterclockwise, so it's positive. The magnitude of that vector is positive. All right, so let me do that. Let me do this over here. So I'm going to write F. Actually, before I do that, I'm going to put in all the components of these vectors, because that'll really save us some time. And we can do this. Hopefully you gain enough experience. You can do this quickly. You don't have to put a lot of thought into it. The more you do these problems, the easier they get. So in this case, we're going to have a x component and a y component. The x component is 4/5 times 500, 400 Newtons. And the y component, and I'll put a negative here because it is in that direction. Although this is a point of complication to a lot of people. There's like 2 schools of thought. You could just write 400 Newtons, and because you drew it in that direction, you know it's a negative value. Other cases, people like to put a negative value. I typically do put a negative value in those. But here we have negative 300 Newtons in the y direction. And over here, we have an x component of this vector, 300 Newtons. We have 400 Newtons down in that direction. And now we can add up all these vectors and get our resultant vector. Eventually, our resultant vector is going to be evaluated. We're going to end up with all these complicated things that are going to reduce to one vector, one moment applied at point O. And we'll use our point O here. And it may seem a little odd. You go, well, you put a force down here. How can that be the same as like having all these forces up here? From the standpoint of the bending moments, the internal forces within the members, different, non-equivalent. But from the standpoint of external forces, the support, what's happening down here, it's okay. We can just put the force down here and the moment down here, and that'll be this equivalent system of this equivalent to this complicated system from the perspective of these external supports that, remember, can't see what's going on up there. Remember, it's a rigid body, meaning there is no deformation. All right, so let's go ahead and do this. So we end up with f r of x equals negative 400 plus 300. equals negative 100 newtons. All right, Fry equals negative 300, negative 400. That'd be a negative since it's downward. So we're going to end up with negative 300 newtons minus 400 newtons, negative 700 newtons. And now we're going to do the moments. So we have actually the vector. I could write the vector. Let's do that while we're here. Negative 700 in the y direction. This is a y. Negative 100 in the x direction. And we could find the magnitude by Pythagorean. 49 square root of something. Big number. Anyways, we're not going to do that. I'll just put in the vector. It's sort of relative. So negative 700y and negative 100 in x. Kind of like that. So 700, 100 in this direction. Kind of makes sense. I buy it. And now we got to get the moment. And it's also going to be applied at that location. So we have the moment r at point O equals, let's start with this one, 200 Newton meters. Counterclockwise, that's positive. How about this one here? We have 400 newtons. And the moment arm, here's the line of action. Our perpendicular distance is 4 meters. So that'd be 1600 newtons. 400 times 4 is 1600. And it's turning counterclockwise, so it's positive. Plus 1600 Newton meters. How about this one? 300 down. And its moment arm is going to be, think of the moment of action. The line of action of the force goes up and down here. Here's our moment arm. 2 meters from here to here. And 300 down will be 600. And it's counterclockwise. So we're going to add 600 Newton meters. And lastly, well, there's 2 more. There's this one. But this one happens to go right through my point O. So that means the moment arm is 0. It has a 0 length moment arm. So it has no moment related to that force. So we'll skip over that one. But we do have this one, 300 times 4 is 1200. And this one is going clockwise, minus 1200 Newton meters. So we can add these up. 1800, 24 minus, you end up with equal to 1200 Newton meters, and it's positive value. And I'll do it in blue. (1200) Newton meters. That's our moment that's applied at that point. So we took this complicated system with it wasn't that complicated. It had 2 forces, 1 couple moment, but we had many moments attributable to these forces, and reduced that all to 1 force and 1 moment that'll give us the same external support reaction as our complicated system. So that's our first exercise in looking at simplification. And in the next discussion, we're going to talk about simplification, where we're only going to have 1 force. We actually reduce everything, including a moment, down to 1 well-placed force. You can't just put the force at point O. We're going to put it somewhere to reproduce this resultant moment. And that's what we're going to talk about next time. So if you have any questions, send me an email, and I'll see you in class.